Welcome to VLSI technology lecture. So in the last lecture, we have already seen about the doping process, which is done by using the diffusion process. Okay, and even we have already seen that various diffusion systems that we have and how we can use the different sources for doing the diffusion process. Okay, so today we are going to look at another technique for the doping. So, as I said in my initial lectures, that we can do the doping by either diffusion process or the ion implantation technique. So, here today we are going to discuss about the ion implantation technique. So, you try to recall this particular figure that I have already explained while starting the our diffusion technique, okay, in which I said that in the case of diffusion, okay, this type of doping profile can be obtained. Okay, so we can have our substrate. Onto the substrate we need to have a particular uh, SiO2 layer, and that SiO2 layer will be acting like a mask. Okay, we need to open a certain window and then we have to go for the diffusion process, and by which we can have the diffusion or the doping of the uh, impurity atoms, okay, into our substrate. And this way we can have this type of impurity profile. Okay, one more thing that I have explained about the diffusion process is that by having the diffusion process, we can form a very deep junctions. Okay, we can have a very deep means because of the diffusivity of our impurity atoms, this impurity can go deep into our substrate. Okay, and generally the diffusion process is a high temperature process. Now, today we have to look at the one of the more important technique, which is, you can say that it is very important nowadays, and most of the doping of the atoms are actually performed by having this ion implantation technique. Okay, so as I said that the ion implantation technique is actually it is a low temperature process. Okay, as compared to your diffusion process, it is a low temperature process. And moreover, it is very important to know that a very precise control over the doping concentration can be obtained in the case of ion implantation as comparison to your diffusion process. Okay, it is very precise. Similarly, in the case of diffusion, we need to have the SiO2 layer as a mask, but in the case of ion implantation, we are having the wide choice of masking materials. Okay, we can have lots of material that can be act as a mask. This particular doping profile already I have explained that in the case of diffusion, you will find this type of doping profile in which the maximum concentration you will find at the surface, okay, at the surface of your wafer. Okay, but in the case of ion implantation, you will find that the concentration of the dopant material will be not high at the surface but somewhere else. Okay, somewhere else, or it can, you can see from this picture that it is maximum at this particular point, and after that the concentration is reducing in both the sides. Either you can go deeper into the material, or even if you go towards the surface, okay, still the dopant concentration is going to reduce. So basically at a certain depth you are going to find the maximum concentration of your dopant. Okay, so now very important thing about this ion implantation is that actually this technique was actually invented by the William Shockley in 1954, but even after its invention, its use in practical life was actually started in the late 70s. Okay, so its use for doping process was actually used very late, even if it was already invented in 1954. So let's see in the ion implantation technique what kind of system that we have and how this ion implantation is basically done. Okay, so what we have said that in the ion implantation technique, we are able to control the our dopant concentration very precisely. Okay, we can do it very precisely. So these are the few ion implantation parameters in which we can see that we can dope the different materials. Okay, different wide range of materials can be doped, and its dose can be varied from 10 to the power 11 to 10 to the power 18 per centimeter square. Similarly, this ion energy actually it is varying from 1 to 400 kilo electron volt. It will depend on at what depth of your penetration that you want, what particular dopant you want to dope. Okay, so it will depend on what should be the energy, what should be the energy of means the ions energy. It will depend on which particular dopant material you want to dope, what will be the dose that you want, what will be the depth you want. Okay, so basically what we can take here is, here you can see in this system, in this system what we have is we should have a particular ion source. Okay, so as I said, in the case of diffusion we can have lots of sources. For example, we had solid sources, liquid sources, and gaseous sources, spin-on sources. In a similar fashion, in the case of ion implantation, we can again have the different sources. Okay, like we have the gaseous sources, we are having the solid sources. Okay, they are having their own advantages. Okay, so most of the time we can here we can means use the gaseous sources as well as the solid sources. Okay, these are the two most prominent sources that we can use. As we know that the gaseous sources in most of the cases they are the toxic gases. Okay, and therefore we need to dilute it before using it in our systems. Okay, so first of all, whatever maybe it may be a source, whether it is a gaseous source or it may be a solid source, basically what we have to do is we have to ionize this particular sources, whether it is a gaseous or it is a solid source. So we need to have a solid source, we need to have a gaseous source, and then we need to bombard a very high energetic electron beam so that this gas sources or solid sources will be able to generate the ions of a particular dopant material. Okay, so that system will be used here. Okay, that system will be used. So basically we need to have a particular hot filament that will be able to generate a very high energy electrons, or we can also use a plasma discharge for this purpose. Okay, so let us assume that if we are talking about the doping of the boron. Okay, then you can see basically boron will be having in the form of Bf2. Okay, and this gas will be available. Okay, into this chamber, and then this chamber, within this chamber we have to bombard the very high energetic electrons, and because of this bombardment, this this gases is going to be dissociated into the ions. Okay, and by that way it may be able to produce B2 plus, B plus, F plus, or these type of ions may be available after the bombardment of the high energetic electron within this source. Okay, so now once the electrons, once the ions are generated, okay, due to the bombardment of high energetic electron beams, then this will be coming and this will be emerging from this particular slit. So after it is coming out of this slit, then as we know that it will be having so many ions, okay, like B2 plus, B plus, F plus, or BF plus. Basically, we have to dope this B plus. Okay, so because of this different charges, okay, different charges and different ions, basically this will have the different amount of charge as well as it is having its different masses. Okay, so to separate out a certain particular ion. Okay, what we need to have is we need to have a magnetic analyzing magnet. Okay, whose function is to means it will be able to turn the path of your ion beams, okay, based on their charge and its mass. Okay, so that as we know that the equation of there will be a Lorentz force equation that the always a moving ions or a charged particle in a magnetic field will be experiencing a force. Okay, and based on the force, its path will get deflected. Okay, so the uh, arrangement of the magnet will be such that it will be deflected in this particular direction. Okay, and obviously when it will be deflected in a like curvature path, it will also be balanced by its centrifugal forces. Okay, so this curvature, the radius of this curvature will be completely dependent on the mass and the velocity of the ions, and obviously it will also depend on the charge on the ions. Okay, so that Lorentz force equation balanced by the centrifugal force can be written, and based on that a different ions is going to be deflected with a different radius of curvature. Okay, and then a particular ion can be selected by controlling this analyzing magnet. Okay, magnetic field intensity can be controlled, and that way we can control a particular ion beams, right? So this way we can control a certain ion beams only that will be passing through this particular slit. Okay, and all other beams cannot be selected. Okay, that should be filtered out. Only one of the particular beam should be selected, and then this selected beam will be accelerated further. Okay, so that it will be able to gain the sufficient energy for the doping purpose. Okay, so once the selected beam is accelerated further, there will be a certain mechanism that will be able to uh, focus or keep these ions in a linear path. Okay, as we know that when there will be a large number of B plus ions, because of having the same charges, there will be a chances that obviously because it is the same charge, it will be trying to repel each other, and uh, it's there will be a spread while traveling. Okay, it will get scattered in this way. Okay, so we need to refocus them. Okay, so we have to refocus them, and then again we have to control its path, otherwise it will go in this fashion. Okay, so basically after having this, there may be a chance during the travel of this electron, this ion beams, there may be a chance that this ion beams may take one electron from their neighborhood, uh, means its neighboring ions, and then it will become neutral. So once if it is becoming neutral, obviously what we know that whenever we have the neutral ions, neutral boron atom, when it is traveling, okay, because of it, it is neutral, it cannot be controlled by having the electrostatic potentials. Okay, so only the effect of electrostatic potential can be made by having a charged particle. Okay, if we are having a charged ion, then only its path can be controlled. We can accelerate it. Okay, we can control, we can scan it. Okay, otherwise if it becomes neutral, then obviously we cannot track these neutral atoms. Okay, so whenever this neutral atoms go to the wafers, okay, whenever it go to the wafers, obviously it is going to dope the wafer. But in such cases what happens is, because of the dopant is neutral, we cannot scan it, and we will not be able to tell how many such atoms are actually being implanted into our wafers, and therefore we will not be very accurately able to tell that what is the actual dose that we have implanted in our wafer. and therefore it is required that these neutral beams, okay, neutral ion beams, neutral beams should be avoided during the implantation. And therefore what we do is, this obviously the whatever be the neutral beams are available, okay, or it becomes neutral during the traveling towards the wafer, it will be continuous in the linear path, okay, because it cannot be deflected due to the electrostatic potentials, okay, its path cannot be deflected. So here we have another deflecting plate, okay, y-axis scanner, you can see here, okay, here we have the x-axis scanner. So these scanners will be required so that this uh, neutral beam can go in this particular direction, okay, and it will be trapped by a beam trapper, okay, neutral beam trapper, it will be trapped by a neutral beam trapper, but the charged ions will be deflected again in a different path, okay, so its path is going to be changed. And because this charged ions will always be constituting a ion beam current, okay, then that ion beam current will be actually measured by this particular circuit, which is also called as the Faraday cup, okay. It is an integrator circuit, and based on this integrator circuit current, we will be able to tell what is the actual dose that have been implanted into the wafer. So this is very important point that we have to remember, why we need to have this beam trap and why we are deflecting the path of the ion beams again. Okay, because once we have done the focusing, okay, due to the traveling, there may be a chances certain ions which was actually initially ion, but later on due to the traveling, it may become neutralized. Okay, and after neutralizing, there will be no further control due to it is not scanned by the electrostatic potential. It will keep on moving in a linear direction, in this particular direction, okay. And we need to have another y-axis scanner in which we need to deflect the path of the charge ion beams, okay, and that charge ion beams will be deflected again, but neutral beam cannot be deflected due to the electrostatic potential, and it will be continuous in this path, and later on it will be captured by this beam trapper, okay. And then only the ion beams which are actually your B plus ions, okay, that is going to be bombarded onto your uh, wafer by actual positioning done by the y-axis scanner and the x-axis scanner, okay. So by y-axis and x-axis scanner, we can control the location of the ion beams, okay. Wherever we want to do this doping, we can perform by controlling the electrostatic potential onto these particular scanners, okay. And then this ion beam current can be measured by the Faraday cup, which is our integrator circuit, and by which we will be able to control or know what is the actual uh, concentration of the dopant material has been implanted. So these are the some of the very important process or system, you can say, that you can understand. So the entire system or the working of this particular ion implanter, you can think of like in this major 5 steps, in which we have the dopant gas followed by a ionizer. Okay, so we need to ionize this particular dopant gas, and then we need to have a mass separator. By having this particular analyzing magnet is actually performing this task of selecting a particular ion beam, okay, a particular ion beam. And then we need to have the accelerator to accelerate our ion beam to achieve a certain doping energy, so that a certain doping depth can be achieved, a certain dose later on it can be dependent on, we can increase the duration of the doping ion implantation, and that way we can control dose, okay. But basically, what is the depth that you want, that has to be decided by based on what ion it is, and what depth we want, okay, what ion we want to dope and what should be the depth, okay. So based on that, we need to control the actual dopant energy. Fine. That is the working of the accelerator. And then X and Y scanner will control the position of the beam, and then it will be uh, wafer will be doped accordingly. So we will be getting a patterned wafer, you can say, or it is a doped wafer we can get. So one thing which is very important, as I said in the previous slide, that we are getting a certain profile of the dopant. Okay. So as we know that all the we are talking about here the silicon wafers into, we want to perform the doping and we want to dope a certain material. So here you can see that when we are means bombarding the ion beams of a certain dopant material, okay, obviously we know that our substrate is having means it is when it is a silicon substrate, this silicon will have a particular arrangement of the atoms. Okay, it will have a certain arrangement of the atoms. So the atoms will be arranged in a certain fashion, so that when this ion beam enters into this material, okay, it will not like that it will always go into a means it will follow a linear path. Okay, what happens is it will enter into the material, it will get deflected many times, its path may get deflected many times, it will be scattered by the uh, atoms available within the our substrate. Okay, because obviously we have the silicon atoms within the substrate, and because of the availability of the atoms in the silicon substrate, or if it is already doped, okay, it may be chances that it may be a p-type substrate and we want to perform the doping of n-type material, then obviously there may be a certain already doped materials or atoms are available, and also the host atom like silicon is available. Okay, so basically I will call this as a target material. Okay, the substrate may be called as the target material, and here we have the ion beam. So basically the target material is having its own arrangement of the atoms, and because of the interaction of the atom with the ion beams, also the interaction of the ion beam with the electrons available in the target material, there may be a chances that the ion beam path will get deflected so many times, and this initial energy of the ion beam, let us say the initial ion beam energy is E naught or E1, okay, let us say, which is also known as the impact energy. Okay, so whatever be the energy will be maximum when it will be impacting onto this particular surface, and once it will start entering or it is going inside the material, it will start losing its energy because of the interaction with the atomic with the atoms within the material and the electrons within the material, and its paths will get deflected so many times, and at a last it will lose its completely its energy will be completely lost, and then it will stop somewhere. Okay, it will stop somewhere. So basically it has traveled so many paths. Okay, you can see that it has traveled so many paths. There are lots of points at which the scattering may take place, some deflection may take place. Okay, and then finally our ion beam is going to stop somewhere. Okay, it is going to stop somewhere. So you can see actual distance it has traveled like this, you can measure this distance, but basically what we have to see is what is the perpendicular distance that our ion beam have traveled, which is measured from the surface. Okay, from the surface. So if it has stopped at this point somewhere, then you can measure from the top of the surface up to this point. Okay, and generally this depth where the ion beam got stuck, or you can say it has stopped, is that depth is called as the projected range. Okay, that particular depth is known as projected range. So that will be your projected range, And I told you that initially that we are going to get a certain dopant profile, okay, in which we are going to have a peak at a certain depth, and then the concentration of the dopant material, dopant atoms is going to reduce in both sides. Either it is go deeper inside the material, or even if you go towards the surface, okay. So we have to look at what are the different stopping mechanism, and how this ion beam is going to stop, okay, so that we have to look at. So this is our ion trajectory and projected range. So I hope it must be clear that it is not always necessary that the electron beams, whenever it enters, it will go in a linear direction. Okay, it is not required that it will go in a straight direction. It not go like straight. Okay, it may enters into this, and then the path may be changed so many times because of the available atoms and electrons within the target material, which is our substrate. So now one more thing that we can see here is about the distribution of the implant, okay, means our dopant material, okay, how it is going to be distributed, okay. So here we can see that you can see here on to the y-axis, x-axis, we are having the depth, okay, up to which our dopant have traveled, okay, the particular dopant energy, okay. There you can see that the distribution of ions implanted into crystalline silicon at an energy of 200 kilo electron volt, okay. So whether it is a boron, phosphorus, arsenic, or your antimony, okay, it is independent of the material, but all the dopants are having the same implant energy, okay, 200 kilo electron volt, okay. So we have accelerated it in such a way that the maximum energy that it has achieved, or you can say that impact energy of this all ions are same, okay. So when we have this impact energy, the initial energy of the ion beams equals to 200 kilo electron volt, the experiment was conducted with the different material, and what they have found is in the case of boron, okay, if you see the atomic masses of the boron, phosphorus, arsenic, and antimony, you will find that the boron is having the least atomic mass, and antimony is the heaviest one, okay. So what we can see that if the ion beam is a lighter ion beam, then it will travel more deeper into the material, okay. It will travel more deeper into the material, okay, more deeper. So you can see that there are certain electrons, certain ion beams of the boron that has reached up to this point, okay, and its peak value is actually coming up to this point, okay. You can see it's the peak value is coming here, okay. Now similarly for the phosphorus, the peak is located at this point. Similarly for the arsenic, the peak is here, and for the antimony, the peak is here, okay. One more observation from this curve what we can make is we can see that the boron, in the case of boron, you can see there is a broader distribution of dopant atoms, okay. You can see it is a broad distribution, okay, it's broad distribution, you can see. But in the case of antimony, if you see this distribution is very narrow, okay. It is having a very narrow distribution, okay. So this is what we can understood from this curve is, so whenever we are having the light ions, okay, whenever we having the light ions, what we can see that we are going to have the even if you said that it is the average distance traveled by the atoms, if it is called as the projected range, let us say that if we said that the projected range, as I said, that it will enter into the material, it will get deflected and scattered by the atoms within the target material, and somewhere it is going to stop, okay. So the projected range, we can also say that it is the average distance actually traveled by the your dopant material. So here you can see that whenever it is a light ions, obviously the projected range will be more, okay. Projected range will be more, okay. Similarly, you can see it is having the broader distribution around its peak, okay. So we are having this peak, and its distribution will be more. Similarly, if we are having the heavy ions, okay, in that case, you can see that it cannot go more deeper into the material. Okay, it cannot go more deeper into the material, and it's projected obviously when it is not able to travel means more deeper into the material, then its projected range obviously will be low. Okay, and obviously because of that it is also showing a narrow distribution, okay, of the atoms. So what is the meaning of the narrow distribution? The doping material will be distributed over a very short amount of range, okay, very short range, okay, but here it is distributed over a very wide range, okay, it is available for a very wide range. Okay, so this picture is actually to have an idea that how the different material is going to behave when we are going to dope it with the same energy. Okay, so with the same implant energy. Okay, so obviously if it is a light atom it will go more deeper, if it is heavy atoms it is going to be means available at the shallower region, it is not going to be means deep inside the material. So this is what we have to understand. If you want to increase the depth of doping for your antimony, okay, what you need to have is you have to increase the implant energy. Okay, that is 200 kilo electron volt is not sufficient, okay, in the case of antimony. If you want this antimony to be doped at this point, okay, you need to increase the implant energy so that the peak can be shifted towards this direction. Okay, so so based on this, as we can see this distribution of the implant, okay, here we can see that basically if we see the distribution, this particular curve can be approximated as a Gaussian curve. Okay, this can be in the first order approximation, we can say that it is a Gaussian distribution. Okay, it is having a certain mathematical form. Okay, so how this can be represented, okay, how this can be represented mathematically, this curve. Okay, so if we want to write this, the concentration of our dopant material, okay, so the distribution of implanted ions where Cx is the concentration of our implanted ions, then that can be given by your uh, Gaussian function. Okay, so that will be Cp exponential minus x minus Rp divided by 2 delta Rp square, and here it is also square. Okay, where you know that this delta Rp is called as your standard deviation, or it is also called as the straggle point. Okay, it is also called as the straggle point. So within this if this is called as the Rp, then Rp plus delta Rp and Rp minus delta Rp, both range will be having or containing the maximum amount of your dopant material, and after that the dopant concentration is reducing drastically. Okay, so how to calculate the total number of ions implanted? Okay, how do we calculate the total number of ions or the dopants that we have implanted? Obviously by having, if we are having the dopant profile, obviously we can go for the its integration. Okay, so we can go for the integration from this point to that point. Okay, so that can be gone from minus infinity to infinity cx dx. Okay, so after doing this integration we have to note down, because it is a Gaussian function, so we have a certain property of the Gaussian function. Okay, so it is going to give you the error function. Okay, or error function you will get like root pi by 2 error function infinity minus error function minus infinity. So based on this property of the Gaussian function, you can calculate the total dose of the your impurity atoms that you have implanted. Okay, so that can be calculated by following this particular property of the Gaussian function. So ultimately you are going to get this equation q equals to root 2 pi delta rp into cp. Okay, so here you can see that our obviously the total dose q is directly proportional to the peak cp. Okay, and it is also proportional to your straggle point. Okay, so this way we can be able to calculate the total dose of our dopant material. And now one more important parameter that we have to understand is, uh, if we want to perform the ion implantation, as I said in my first slide, okay, that in the case of diffusion, when we perform the doping, okay, what we need to have is we need to have a certain masking material. So in case of diffusion, what we use is we use the SiO2 layer. Okay, SiO2 layer that will be able to act as a mask. Okay, in case of your ion implantation, you have to remember that, for example, in case of ion implantation, we most of the time we use photoresist as a masking layer. Okay, it doesn't mean that the our SiO2 cannot act as a mask. SiO2 is also acting as a mask, but we need to take a very thick layer. Okay, in case of doping due to diffusion, using diffusion method, a very thin layer of SiO2 can also be act as a mask. But in case of ion implantation, as we know that the ions, high energetic ion beams, will be able to penetrate the SiO2 layer. Okay, uh, we need to have a thick layer of the SiO2, or a particular thickness that we need to have. Otherwise, your SiO2 mask cannot be able to control the dose. Okay, it cannot able to stop the your ion beams, or you can say the dopant material, wherever it is available. Okay, so we need to have a particular thickness. Okay, you have to remember one more point is that your metal layers are a very good stopper or a very good mask for your ion implant beams. Okay, in the case of ion implantation, if you want to stop the beams, okay, ion beams, any thin layer of the metal will work very well. Okay, similarly, a photoresist layer is also working very well. Okay, so we need to have a first of all, we need to know the property of your masking material. What will be the distribution of the your masking material if we go for the doping process using the ion implantation? Okay, so that should be known beforehand. Okay, if you don't know what is the distribution of the ions when we go for the implantation, then you could not be decide what should be the actual thickness of that particular mask. Okay, so let us suppose that in if we want to take SiO2 layer, it is not like just only SiO2 layer. If any layer you can just consider, we I'm just calling it as a mask. Okay, here I have just exaggerated the thickness. Okay, I have just exaggerated the thickness just to match this thickness with this curve. Okay, so don't confuse that it is having a very thick layer of the mask, and here we are having the substrate whose thickness is very less. Okay, it's not like that. I have just exaggerated this particular picture to explain the concept of how to calculate the thickness of the mask. Okay, that will be sufficient to stop the ion beams, so that the places where you don't want to have the doping, that should be prevented. Okay, that should be prevented. So how it can be prevented, that we have to look at from this curve. So let us suppose that this particular ion distribution in the mask is already known. Let us suppose that we already know this. This is the distribution of the ion. As I said that the ion distribution in the target material is almost given by the Gaussian distribution. Okay, so let us suppose that we have the Gaussian distribution, and it is already, this distribution is known for the masking material. So let's assume that we are having a mask whose thickness is xn. Okay, and wherever the mask we have placed, okay, what we need to have is, what we want is, under the mask there this ion beam should not be able to reach. Okay, it should not be able to reach, so that the this means the doping should not take place under the mask. Okay, so to avoid that, what is the condition? The condition is that if let us suppose that we have the silicon and it is already like it is a p-type substrate, for example, and we want to implant the n-type dopant. In that case, under the mask, if you don't want to uh, have the doping, then obviously let us suppose that if we call this already doped substrate concentration is cb, okay, which is we can call it as like cb. Okay, let us suppose that the already doped silicon, which is a p-type dope material, if it is background concentration of the p-type dope material is cb. Okay, so it is a cb, we are calling it as a background concentration of our target material. So when we are going for the doping, okay, and we want this mask has to stop the ions, okay, then obviously when you bombard this wafer, okay, your ion beams will travel through this mask. Okay, and after traveling through this mask, due to different stopping mechanisms, okay, your ion beams is going to stop or stuck somewhere. Okay, so first it will stuck in the mask itself. Okay, so obviously it will be following this particular doping profile, okay, into your mask. So what we can see here is its peak is somewhere here. Okay, its peak is somewhere here. Here you can see its peak is somewhere here, and then this distribution is like this, and then there is a little amount of dopant, okay, which was able to penetrate the mask and it enters into the target material, means your substrate. So this amount of dopant has reached to your silicon. Okay, so let's assume that this amount of dopant have reached to your silicon. So now once this amount of dopant have reached to our silicon, what we are assuming is, what we are saying is, for efficient masking, okay, for efficient masking, the amount of your means the concentration of your dopant that has reached to your silicon, okay, that concentration, if I call it as c star xm, okay, because I am calling it as xm is our depth of your or your thickness of your masking material, okay, masking layer. So after xm distance or xm depth, okay, whatever be the concentration, that concentration of the dopant material, I'm calling it as a c star xm. So what I'm saying is this c star xm should be less than, or maximum at worst condition it should be equals to cb. Okay, it has to be less than cb. If it is less than cb, the concentration of the dopant material, dopant concentration, okay, is less than the background concentration of the silicon. Okay, therefore the concentration or the type of the silicon substrate doesn't changes. Okay, if this condition prevails, you remember that. Okay, because what we are saying is the dopant concentration at this point is less than the concentration background concentration of the silicon. Okay, when it is less than that, obviously it will remain p type, it doesn't going to change its type. Okay, you remember that. Okay, it is not going to means turn into n type. So what we are saying that the maximum possible thickness you can achieve is when it is equal. Okay, so it can be equal. So if you are keeping it equal, then obviously when the background concentration and the concentration of the dopant become equal, at that time it will become a neutral substrate. You remember that. Okay, so by having this particular equation, what we can do is we can calculate what is the thickness of the mask that has to be there to act as a efficient mask. Okay, to act as a efficient mask. So here I have taken all the values corresponding to the mask. Okay, because it should be a Gaussian profile, I have taken it to be a Gaussian profile. All the parameters is same. Okay, the only thing is I have taken this star mark. Okay, just to reflect that this particular equation is being written for the masking material rather than the target material, okay, your substrate. So after having that, what we can set is we can set C star xm equals to CV, and then we can solve it for the xm because xm is the thickness, okay, of our mask. So just you put this one, okay, into this equation, okay, Cxm equals to Cv, and then you try to solve it. It is simple to calculate. You will be able to calculate that the xm is equals to Rp star plus delta Rp star root over 2 ln Cp star by C. Okay, and later on you can turn out this equation into this form: Rp star plus m. I am calling this entire factor is equals to m. Okay, so obviously you can see that first of all we need to know the distribution profile of the dopant material into the mask, and after knowing that we can calculate the thickness of your mask based on following this equation. Okay, based on following this equation. Okay, based on this we can calculate what will be the thickness that should be there to avoid the penetration of the dopant material through the mask. Okay, now you can see that if we wish to calculate, let us suppose this amount of impurity is already penetrated into your substrate. So if you want to calculate what is the total dose that has been incorporated into your target material under the mask, that can be calculated by calculating the again doing the integration. Okay, so as we already have this equation, okay, so that equation you have to integrate from this xm to infinity. Okay, initially we did it for minus infinity to infinity to calculate the entire dose. Just to calculate this amount of dose, what we can do is we can go for integration from xm to infinity. Okay, and then after calculating this one, okay, you can show it like because again we are having the for this particular Gaussian function, we have this property for when d to when the power is means the limit of the integration is varying from d to infinity, you will get this particular equation which is a complementary error function, and by following this one you can calculate what is the total dose by having this equation. Okay, you try to verify that. It is very simple to get this equation in which you can calculate what is the dose of your impurity that has entered into your target material. Okay, that you can calculate. So this way we are able to calculate what should be the thickness of the mask. Okay, and it is a very crucial parameter, you remember. Okay, now we have to look at as I said that this ion is have to means has to stop somewhere. Okay, so as I said this ion has to stop somewhere. I told you initially that because in the target material which is our substrate, okay, the substrate is made up of, it is already made up of silicon. If it is already doped, then obviously it is also containing a certain doped material, okay, already doped material. So because of the availability of the different atoms, silicon atoms, which is our host atom, and also the already available doped atoms, there is a chances that these atoms and the electrons are going to obviously interact with the ions. Okay, so when it interact with the ions, because it is a charged ions, okay, charged particle, due to the interaction there will be a chances that there will be a net transfer of energy from ion to your crystal lattice. Okay, there may be a chances that the ion is going to transfer its energy to the crystal. Okay, and sometimes this interaction may be such that it will be able to it will be able to damage your crystal as well. Okay, sometimes there is a chances that this is going to be damage your crystal, and sometimes it is not going to damage your crystal. Okay, so that you have to remember. Here we are having the two basic mechanism of your stopping. Okay, so you remember that this particular theory actually developed by these three scientists. One more important thing is that actually we already know there are so many theories about the atoms have been developed, like in the 1911 Rutherford was also explained a certain theory how the ion beams are going to interact with the any material. Okay, similarly, after Rutherford, there were one more scientist whose name was Bohr. Okay, Bohr also attempted to unified theories of ion stopping by matter. Okay, and he was also giving a certain hypothesis that how the energy of the ions are going to be lost, and they have still means Bohr have also told that these energy of the ions can be lost due to nuclear stopping or electronic stopping. Okay, so there are so many people have worked to come out to a particular conclusion. Okay, like after Bohr, there were other scientists also who have already worked upon that. Like there were one more scientist whose name was Bethe. Later on, Bloch was also worked for this particular thing. Then Fermi have also worked. There were one more scientist, Teller. Okay, Teller was also worked for how this ions are going to interact with the material. Okay, at the last what happens is these three scientists are actually work together, and they have given a particular theory, like Lindhardt, Scharf, and Kyoto in 1963. They have given a certain theory, and that theory is popularly known as the range theory. Okay, LSS range theory. Okay, so that is they have tried to explain the interaction of the ions with the matter. So whatever be the means ions, whatever be the matter, okay, they have able to explain and how to calculate the interaction of these materials, ions with the material, and how to calculate those stopping energies. Okay, so basically what we have understood is that the the ion beams is going to enter or penetrate into the substrate, and obviously because the substrate is having its own arrangement of atoms. Okay, it is going to collide with the lattice atoms as well as the electrons surrounding the atoms. Okay, so because of this collision between the lattice atoms and the electrons, or the interaction you can say, there will be a gradual loss of energies, okay, of your ion beams, and finally it is going to stop somewhere or stuck somewhere in the material. This way how your ions are actually going, some ions are going deeper into the material, some atoms are not going more deep into the material, but it is stopped somewhere. Okay, so basically there are two basic mechanism. One is called as the nuclear stopping, and another one is called as the electronic stopping. Okay, so as the name suggests that we are having the ion, okay, which is a positively charged ion, it is going to uh, stop, or it is going to collide with the nucleus of your silicon atoms or any other atoms available into the target material. So when it is going to collide with this, okay, obviously you know that when it is colliding with the positive nucleus, okay, it is also having a positive charges. Okay, then obviously it is going to have a collision, and there will be a net transfer of energy that is going to be take place, and it will be depending on the masses of the two means particles. Okay, that is going to decide in what factor the energy of the particles is going to be divided. Okay, so basically it is going to interact or collide with the atoms, and after collision with the nucleus of the atoms, its path of the ion is going to be deflected. Okay, it will travel in a different direction, and a certain energy will be transferred to the crystal lattice or to the atom. Okay, so now you can see because of this, there will be a scattering of the atom is going to take place. Scattering of the scattering of the ion beams will take place, and that also causes the damage to the crystal. Okay, damage to the crystal. So this way your nuclear stopping will take place. Nuclear stopping will take place, and another stopping mechanism is your electronic stopping. Okay, so in the electronic stopping here you can see that in the case of electronic stopping, generally these ion beams which are traveling into the material, that is going to interact with the electrons. Okay, electrons which is being orbiting around your atoms. Okay, which is orbiting around your atoms, so it is going to interact with the electrons, and after the collision with the electrons, uh, again it will depend on whether it is a non-local interaction or it is a local interaction. Okay, it will depend on what kind of interaction it is. Okay, there may be a chances that there will be a very little chance that the path of the ion beam may get deflected, or sometimes it also doesn't get deflected. It will depend on whether it is a local or non-local interaction with the electrons. Okay, and this way your ion beam is going to stop or lose its energy. Okay, one very important thing that you have to remember is generally the nuclear stopping. Okay, this nuclear stopping is a elastic collision. Okay, so what we are saying that, let us suppose we are having a particular ion, okay, which whose energy is even, initial energy is even, and it is having its initial mass is equals to m1. Okay, and we are having another means nucleus, okay, whose mass is m2. Okay, so generally our ion is traveling, so it is having a certain energy due to its means kinetic energy due to its motion, and normally we considered the uh, nucleus as a stationary entity. Okay, so this particular nucleus will be your stationary particle. Okay, so now once this is traveling, okay, based on the distance between the two, because they will be having the same charges, okay, like positive charges and positive charges, it is going to have a certain interaction between these two. Okay, and because of this interaction, there will be a net exchange of the energies. So generally, this exchange of the energy can be calculated by following the two particle theory, following the classical physics. Okay, so that can be calculated by using the classical physics. Okay, and two particle theory. Okay, so that can followed, and we can calculate what is the net exchange of the energy. So basically, this particular collision, if it is having a head-on collision, okay, so it is not necessary that it is going to be always a head-on collision. Sometimes it will be a head-on collision. So whenever it is a head-on collision, in that time there will be a maximum energy loss, and you can get this maximum energy loss equals to delta A, which will be equals to 4m1 m1 m2 divided by m1 plus m2 whole square multiplied with the E1, where E1 is the initial energy of the ion, or you can say it is the impact energy of the ion. Okay, here you can see that this particular case, when it is going to interact with the nucleus, it will be deflected towards a different direction. Okay, so it can go into this particular direction. So this way it is going to change its path. Okay, it is going to change its path. Similarly, we can again calculate what will be the its scattering potential. Okay, so what will be the scattering potential by considering that the nucleus is also surrounded by the certain electrons. Okay, so the net positive charge onto this nucleus, okay, that has to be considered, because it is also containing a certain electrons which is orbiting around the nucleus. So we have to take that into consideration, and we can calculate that this means scattering potential will be given by this particular equation, where the Z1 and Z2 is the atomic number of this ions. Z1 is the atomic number of the ion, and Z2 is the atomic number of the our atom. Okay, so this way we can calculate the scattering potential, and further we can calculate the nuclear stopping power. So this is our result of simulation, computer simulation. Okay, to fit the nuclear stopping power, okay, with the experimental results. So this you can find in any of the books. You will find that the nuclear stopping power is the simulated result is actually given by this particular equation. So this way we can calculate the nuclear stopping power, and then we can calculate this equation whose unit you can find it as we have calculated in the form of electron volt centimeter square. So its unit will be electron volt centimeter square. Now we have the electronic stopping. So in the electronic stopping, basically it is a Coulombic interaction, but it is inelastic. Okay, it is inelastic. So in this case, what happens is one particular ion beam will enter into the material, and when it will enter the material, obviously because of having a certain charges on it, this ion is going to polarize your material. Okay, so once the polarization is taking place, what happens is sometimes it happens that the ion is traveling, and it is actually all the nearby electrons are attracted towards it. Okay, and that force is called as the drag factor. Okay, it is a dragging the electrons. Okay, so once there is a drag between the electrons, obviously because of the net force of attraction due to the drag, okay, it will try to retard the kinetic energy or its velocity of the ions. Okay, it will try to pull this ion. Okay, so once it will start the pulling of the ion, then obviously its velocity will reduce, and it is going to lose certain energies. Okay, similarly in the case of local electronic stopping, what happens is here the ion is going to interact with the particular electron. Okay, orbiting around means orbiting around nucleus. Okay, so it is going to means it is going to collide with the electron in a particular electron, and after collision what happens is it is going to uh, give off certain means energy to the electron, and by taking certain energy from the ions, this electron will be promoted to higher energy state, and due to this there is a chances of means scattering of the ion, and its path will get deflected. So normally one thing that we have to remember is that the deflection of the path due to this local electronic interaction, okay, as compared to your nuclear stopping, this deflection is very small. Okay, normally it is very small. Fine. So this way it is going to interact. So here we have to clearly understood that in the non-local case, the electrons which are dragging this particular ion belongs to different atoms. Okay, it is belongs to different atoms. It is trying to pull your ion. Okay, and because it is not localized electron, it is the electrons belongs to your entire material, and therefore this is called as a non-local interaction of the electron with your ion. But in the case of local interaction, what we are saying that this ion is going to interact with a certain electron, a particular electron, and then it is giving certain energy to the electron, so that the electron will be promoted to higher energy state, and its path will get deflected. So this way, ultimately, we are means our ions are actually losing the energies. Okay, so ultimately it is losing its energy. So normally, whether it is a non-local interaction or a local interaction, the energy loss to electronic stopping is normally given by this equation. Okay, it is normally given by this equation. Okay, so this way we have to know that there will be a ion means nuclear stopping. There could be electronic stopping responsible to stop your or to lose the energy of the ion beams. Okay, so this way your ion beams are actually losing the energy. So basically what we can see that we can see the average energy loss of ions per unit distance if you want to calculate. So once it is traveling towards means deeper into your material, what is the average energy loss? So if we calculate average energy loss per unit distance, then it will be denoted by dE upon dx, and that can be given as minus n multiplied with the power used for nuclear stopping and power used for electronic stopping. Okay, so that has to be added together, and because we have calculated it for a particular electron, then it has to be calculated for the this number n, which is nothing but the atom density of the target. Okay, it is atom density of the target. So by multiplying this factor, we will be able to calculate what will be the energy lost by your ion beam per unit distance as it travels through your material. Okay, and if we wish to calculate what is the total range that your ion beam is going to travel, then obviously we have to do the we can write this dx here. You can go just try to modify this equation, and we can calculate this range by calculating it over distance 0 to r. Okay, so after doing this integration of the dx, okay, over the range 0 to r, you can just try to modify this equation. You will be getting 1 upon n dE upon SNE plus SEE. Okay, and then you have to integrate the same thing. Okay, we have to integrate the same thing from its initial energy to your final energy. Okay, and after having this uh, particular integration, we will be able to calculate the range. So after this, I hope this discussion you must have got something. Okay, how this ion implantation is done, and what are the different terms associated with it, how to calculate the thickness of the mask, what will be the distribution, what will be the different mechanism of your stopping. Okay, that you must have understood. Okay, in the coming lectures, I am going to tell you subsequent one more important topic. I will be discussing about the channeling. So, so till then, try to understand this concept. Go through this lecture. Okay, if you have any doubt or queries, you can please uh, write in the uh, comment box. Okay. So thank you for watching. I will be discussing the next topic in the coming lectures. Thank you for watching.